First of all, I would like to thank the organizers and the program committee for allowing me to talk about such a foundational topic. And this work that I'll tell you about is a collaboration with other people from Perimeter Institute, namely Belen Sainz, Ravi Kunjwal, David Schmidt, and Ellie Wolf. And before I actually explain to you what this title means and what we actually did in our work, I would like to give you some motivation for why are we doing what we are doing. So let's look at that. In quantum foundations, a lot of the work that people do concerns a question of how to derive quantum theory from certain axioms or some postulates you might come up with. And this derivation of quantum theory can be of two kinds. So one kind is to try to derive the mathematical structure of quantum theory. And the other kind would be to try to derive the statistical content of quantum theory. So that would be, what are the quantum correlations, or in other words, the possible probabilities predicted by quantum theory. Our work mostly concerns the latter, the derivation of the statistical content of quantum theory. But as you will see, it does so by actually connecting some ideas from the structural derivations of quantum theory. So the broad question we are answering is, can we identify the statistical prediction of quantum theory from some nice principles? And by nice, I mean some principles which are well motivated or maybe intuitive, but I will not make it more precise. That's kind of what it is. So there's been a lot of work in this direction in quantum foundations, and in trying to come up with principles that would do the job, there has been an ongoing challenge, kind of recurring theme, which is that most of the principles that have been proposed do not actually pick out the set of quantum correlations, but in fact there is a strictly larger set of correlations called almost quantum, which was introduced in this paper, which also satisfies these principles that people maybe thought that would be the essence of quantum theory. And so our work is basically a kind of suggestion on how you might overcome this challenge. So in particular, we look at a principle, the Specker's principle, which actually pertains to the structural derivation of quantum theory. So it pertains to structure of measurements rather than the correlations. However, we've shown that this principle actually is inconsistent with the almost quantum correlations. And in the words of Ernst Specker, the principle can be stated loosely as such: if we have several questions such that we can answer any two of them at once, then we can also answer all of them. And I will make it more precise later on, but this is kind of the slogan. Okay, so now let's see how could we arrive at such a conclusion. Here's the outline of the talk. So first of all, I will define and describe some of the necessary ingredients that we will need to actually talk about this issue. And then we will go through the argument in quite a short time. We will show that the Specker's principle has some consequences for certain experimental scenarios, in particular for the probabilities of certain outcomes that you can get in some experiments. And in particular, we will show that in certain experiments, in certain kinds of experiments, there will only be classical outcome statistics allowed. And I will explain what that is, as long as we want to satisfy Specker's principle. And then we will go on and we will show that in some of these experiments, there can be almost quantum correlations which are non-classical in the sense that I will define, and therefore measurements that satisfy the Specker's principle will not be able to generate all the almost quantum correlations. So that's a contradiction that we will find at the end. Okay, so let's go through some definitions. First of all, I want to define what I mean by compatible measurements, because that is a notion that will feature in a statement of the Specker's principle. And if you've been to Andreas Blum's talk, then you would have seen this. I'll try to be brief. So the measurements M1 through Mn, we will say that they are compatible or jointly measurable if there is some single measurement M prime, say, which can simulate these measurements. And what I mean by simulating is that we can post-process the outcomes of M primed and get any of these original measurements, M1 through Mn. If you remember from the yesterday's talk, this is also equivalent to the fact that we can marginalize the outcomes of M prime and get the original ones. So I'll not go through that again. And from standard quantum theory, we are fairly familiar with the fact that if we have certain observables and we want to be able to say that we can simultaneously measure them, then that is equivalent to their commutativity. And in fact, this notion of compatibility, if we apply it to projective measurements in quantum theory, then indeed this compatibility corresponds to just the commutativity of the projective measurements. And now, there's one important property that I will need for compatible measurements, and that's this one. It is that the marginal statistics of measurements which are compatible will admit some joint probability distribution that then marginalizes to those individual statistics of those compatible measurements. And we will use this later on. This is fairly straightforward because the joint probability distribution is just the probability distribution of the outcomes of the joint measurement M primed. And okay, I will skip this point. It's not important. Okay. Now, as I said in the beginning, there are kind of two ways of approaching the axiomatization or derivation of quantum theory. And even though the analogy does not really hold on the nose, there is similarly some kind of dichotomy between describing experimental scenarios. And one of the ways of describing them is in kind of structural way, using the compatibility structure of measurements. And the other one will be more statistical, which will only pertain to the outcome statistics or probabilities of certain outcomes. So let's start with the compatibility one, and we will try to connect them to make certain inferences. So here I have an example of a compatibility hypergraph, which is a notion that is used to describe experimental scenarios in the more structural way. So here, the vertices of this hypergraph, M1, M2, and M3, they correspond to individual measurements. And the hyperedges, which encircle them, these correspond to sets of compatible measurements. So here, in this example, we have 3 measurements, and any pair of them is compatible, but we do not necessarily require that actually all 3 of them are compatible. So this scenario is called the Specker's triangle. And in order to be able to connect it to the kind of statistical description of the experimental scenario, we have to talk about the possible outcomes, the possible events that can occur when we perform these measurements. So for each pair of these measurements, we can know that we can only measure 2 of them at a time, because only pairs are compatible. So for each pair, we have 4 events, as long as we assume that these are binary measurements. So in total, we will have 12 possible events, because we have 3 pairs. And now, every choice of 2 measurements, so every choice of a sequence of compatible measurements, will yield a certain normalization constraint. So the normalization will be that summing the probabilities of all the possible outcomes of that sequence of measurements is just going to be 1. And so here, I drew the 2 different descriptions of the same experimental scenario. It's not really important what's exactly the structure. I just want to illustrate the connection. So on the left-hand side, we have the structural one. So there's measurements and compatible sets of measurements. And on the right-hand side here, what's called the events-based hypergraph, we have the 12 events. Those are the vertices, these circles. And the hyperedges here are those normalization constraints. So each of the hyperedges on the right-hand side imposes a normalization constraint on the probabilities of those events. So just to illustrate what those events are, for example, this top left one. So I wrote here 0, 0 given 1, 2. So that just means that this event corresponds to outcomes 0 and 0, given that measurements M1 and M2 were performed, and so on. It doesn't really matter which one is which for our purposes. And now, in both of these pictures, we can talk about the probabilistic models. So those are probabilities assigned to outcomes we could get in an experiment. But it's actually a little easier to talk about it on the right-hand side, so that's what we will do. A probabilistic model is an assignment of probabilities to each of those events. So each of the vertices, we assign a probability. And we also require that for any hyperedge, the probabilities are normalized, just like I said. And now, we can use these probabilistic models to study how different theories can differ, or maybe how making certain assumptions or imposing certain principles affects the statistical content of a theory. So let's do so. In order to compare these theories, we will make a certain coarse graining. So we will not use all the information, but we will somehow collect all the allowed probabilistic models for a given theory. So, for example, if we want to assume a non-contextual theory, if you know what that means, or here I call it classical, it yields these probabilistic models. So we would say that a probabilistic model is classical if it can be written as a convex combination of just assigning deterministic values to those vertices. And this property, in fact, is equivalent to the existence of a joint probability distribution for the measurements in the structural picture. We will get to that later. Yes, so the vertices represent outcomes of possible sequences of measurements we could perform. That's right. So to each of those outcomes, we assign a probability that we could possibly observe in a sequence of experiments that we would perform. And so apart from classical models, we can also define what we mean by quantum models. So a probabilistic model would be quantum. If there is some quantum state, density matrix rho, and some family of projectors, so there's pi v, one for each of the vertices, such that the projectors are normalized along each of the hyperedges. So they give us valid projective measurements for each of the hyperedges. And furthermore, the Born rule just gives us the probabilities. So this would be the the quantum models. And now finally, we can get to the almost quantum models, which correspond to the idea of the almost quantum correlations. And the definition is like this. A probabilistic model P would be almost quantum if there is some quantum state, rho, and again, a family of projectors, one for each vertex, such that now these projectors are subnormalized along each of the hyperedges. And again, the Born rule just gives us the probabilities. So this is how we would define almost quantum. And you can see that any almost quantum probabilistic model is also quantum, but not necessarily vice versa. And in fact, it is true that there are almost quantum models which are not quantum for certain scenarios. Sometimes they coincide, but sometimes there is a gap. OK, so let's now actually define or describe the Specker's principle in more concrete language, in particular in the language of compatibility. So the Specker's principle, what it says is that if we have a set of measurements and any pair of them are compatible, so you pick any two of the measurements in the set and they are actually compatible, they have a joint measurement, then it should be the case that actually all of those measurements in that set are compatible. So there is a single joint measurement that can simulate all of those measurements in that set, not just the pairs individually. So this is the content of the Specker's principle from the title. Now, what we want to study is the various consequences this principle has for the statistics or for the probabilities a theory that can arise from a theory. So you see that the Specker's principle by itself really applies to the structure of measurements, the compatibility structure, but we want to talk about the probabilities, the statistics. So one possible translation is this principle. It's called consistent exclusivity, but the name is not so important. Basically what it says is that whenever we have a set of events, so now not measurements, but set of events, set of outcomes, such that any two of these events are exclusive, so what that means is that they cannot both occur at the same time, then adding the probabilities of all of these events cannot exceed 1. So this is a bit of a strange principle, but it actually follows from the Specker's principle. And how much time do I have, actually? OK, so since I have enough time, I will go through an argument for why Specker's principle actually implies this principle of consistent exclusivity. Maybe that will make it more precise what it actually means as well. So here, I will do it for just a set of 3 events. And the argument is similar for more events as well. So here, the events we are interested in are V1, V2, and V3. So those are 3 events, and they are pairwise exclusive in the sense that any 2 of them appear in one hyperedge. And what that means is that they are possible outcomes, distinct outcomes of some measurement. And therefore, they cannot occur both at the same time. And they are pairwise exclusive as a triple. Now, there's also these vertices W1, W2, and W3. And those are just the aggregate outcomes. So for example, W1 would be the outcome of this bottom measurement, which corresponds to neither V2, neither V3 actually happen. So there's all the rest. But we are not really interested in those, actually. OK. So now, from this hypergraph, we can see that there are certain measurements that we can construe. There's M12, which is basically this top right one. It has outcomes V1, V2, and W3. And similarly for the top left and the bottom one, there's M13 and M23. And once we have these, we can coarse grain those outcomes and get new measurements. So there's a measurement M1, which occurs if we coarse grain, for example, V2 and W3. So that would be this case. So this just means it's either V2 or W3. We don't really care which one. But similarly, we can construct it from this top left measurement, and that's by coarse graining V3 and W2. And this will be the same measurement called M1. And similarly, we can do the same thing for V2 and V3 and get measurements M2 and M3. And we get this picture that we've already seen, which is the Specker's triangle. We have 3 measurements, M1, M2, M3, and they are pairwise compatible because, for example, you can see up here that M12 is in fact a joint measurement for M1 and M2. We can obtain M1 and M2 by just coarse graining the outcomes of M12. And similarly for the other ones as well. So now, if we assume that Specker's principle holds, it follows that we can replace this by a single joint measurement, because any set of pairwise compatible measurements is in fact jointly compatible. And from that, it follows that there is a single joint measurement, M123, which can simulate all of those M1, M2, and M3. And it must have outcomes V1, V2, V3, because those were pairwise exclusive to begin with. And now, from this, it directly follows that the probabilities of V1, V2, and V3 have to be bounded by 1. But you see that we had to assume that Specker's principle holds. This gives us the principle of consistent exclusivity, but it doesn't follow by fiat. We have to assume Specker's principle to get that. So that's what this implication gives us. It turns out that this principle, consistent exclusivity, anyway, the consistent exclusivity is actually satisfied by all of these almost quantum probabilistic models that I defined before. And this has been shown in this paper, where also you can find a big discussion and, in fact, all the definitions related to the events-based hypergraph that I was talking about. So if you're interested in that, you can have a look there. So the consistent exclusivity alone seems to suggest that maybe Specker's principle also cannot really distinguish between quantum and almost quantum. But what we have found is that there's other consequences of Specker's principle for the correlation. So there's this principle of pairwise sufficiency, which is what we call it, which seems to trivially follow from Specker's principle. It says that whenever we have probabilistic models generated by measurements, which themselves are pairwise compatible, just like in the Specker's principle, then this probabilistic model has to be classical. And the reason why this follows trivially is that by Specker's principle, if the measurements are pairwise compatible, they have to be jointly compatible. And as I said in the beginning, in relation to compatible measurements, whenever we have a set of compatible measurements, it follows that the marginal statistics of those measurements admit a joint probability distribution. And admitting a joint probability distribution is just the same as the fact that it is a classical probabilistic model. So that's why the pairwise sufficiency follows from Specker's principle. So now the question is the pairwise sufficiency enough to separate quantum from almost quantum? Well, you probably could have guessed that the answer is yes. And how do we find it? Well, there's this counterexample. This is the simplest counterexample that we could find. It consists of 4 measurements. So there's M1, M2, M3, and M4. And they are pairwise compatible. So any pair of them is compatible. And under the assumption of Specker's principle, all the probabilistic models you could obtain from this scenario, if you once you translate it to the events-based language, the events-based hypergraph, all the probabilistic models have to be classical if you assume Specker's principle. However, if you perform some convex optimization, then you can find that there are, in fact, almost quantum models in this case, which are non-classical. So the principle of pairwise sufficiency is not satisfied by the almost quantum models, and consequently, the Specker's principle is in contradiction with almost quantum correlations as well. So the upshot of all this is that whenever we have some measurements which happen to satisfy Specker's principle, they cannot generate the whole set of almost quantum correlations. And with this, I would like to conclude. So one of the consequences of all this is that the Specker's principle becomes kind of reinstated as a possible principle that could help pick out the quantum correlations from the set of all correlations, or maybe more reasonably, it could be some device-independent consequence of Specker's principle at the level of correlations. And this is despite the fact that what has been thought as like the direct translation of Specker's principle to correlations, the principle of consistent exclusivity, only picks out the almost quantum correlations and doesn't give us the quantum set. Another consequence is that if in any theory, for example, a general probabilistic theory, there are some measurements which could possibly generate the whole set of almost quantum correlations as it's defined, then it has to be the case that some of these measurements have to violate the Specker's principle. And finally, if you think that Specker's principle, as it's stated, should be considered a necessary condition for some sensible theory to satisfy, then it follows that the almost quantum correlations are not really physically meaningful. Thank you.
Time for questions from the audience? Yeah.
Hi. So my question is, let me just check I understand. So you have Specker's principle, and you find this state that comes from the almost quantum set of correlations, and it violates Specker's principle. Yeah?
That's right.
But the set of quantum correlations is a subset of that, so I didn't quite follow if we know that quantum correlations have to satisfy Specker's principle or not.
So the way that the quantum correlations are defined, they are defined through the projective measurements, if you remember. So there were those projectors assigned to each of those events.
Yeah.
And it is not very hard to check that the projective measurements in fact satisfy Specker's principle. So because we have defined quantum correlations through projective measurements, and projective measurements satisfy the Specker's principle, so it is enough to check the commutativity, which is a binary property, is a property which reduces to just pairs, then it has to follow that Specker's principle is satisfied by quantum correlations in any of its consequences for the, at the level of correlations.
So you claim that counterexample shows up in the case where you have 4 different measurements. Do you have a concise description for what the density matrix and PVMs are for the counterexample?
No. We've done the convex optimization, and that gives you certain value of some inequality, but we haven't really constructed the explicit matrix and the measurements.
Are there more questions?
Thanks. Do you know of like what's the state of arguments for Specker's principle from other assumptions?
Not really. No, I don't. Yeah.
Anyone new?
So if I try to like drag my memory back, there's this paper by Miguel Navasquez and others where they have this like hierarchy of different sets of correlations that are defined by different SDPs. And so where does this kind of counterexample sit with respect to that hierarchy? Like, do you...
So in that hierarchy...
So there's like Q1 and Q2 and so on and so forth. So are you able to see if it sits somewhere...
So it is an interesting question to, once we see that almost quantum correlations are not, for example, this pairwise sufficiency principle, almost quantum correlations are larger than the correlations which are allowed by this principle, or at least not necessarily included in there. It is a valid question to ask, what is the set of correlations which is implied by Specker's principle or some of its consequences. And we haven't really explored that question in great detail. The hierarchy that you mentioned, so almost quantum correlations appear there as one level of the hierarchy, I think. So because of the inclusion conditions, you could probably say something about how from this result, you could infer other non-inclusion conditions between different levels of the hierarchy and the correlations allowed by Specker's principle, for example. But what is the actual set of correlations allowed by that principle? We don't know.
Yeah. So I mean, that's almost like anyone else? Or I can kind of finish that question maybe a little bit. It's just that, okay. But surely it's a straightforward thing then. If you if you've got the SDP solver set up, so just run through the whole hierarchy and see if your example sits inside the hierarchy or not. I mean, you've basically told me that it sits within one of the levels, but can't you just iterate through them and see if it sits in all levels or if there's a level at which it fails? And that gives you like an ansatz for a set of things that contain Specker's.
Yeah, you could do it for each of the. I think you could do it for each of the, say. Okay, so let me think. So when we did this optimization, we optimized a single inequality, which is basically a facet of the classical polytope. But if you were to do the SDP, it probably would give you in the end whether it is included in these levels of the hierarchy. So we didn't actually need to do the full SDP here because we just optimized over one inequality. But yeah, we haven't done that, and I'm not sure how much it would actually give us. I mean, it would definitely go in the way of answering that question of what is this set of correlations, but that's not really the question we were asking, actually. Yeah.
All right, so let's thank Thomas again for a nice talk.